This is part 2 of the implicit differentiation video. So we're now on our 6th example. Have you ever encountered a function wherein it involves an expression where you have a variable in the base and in the exponent? So in this case, these are both variables, also the base. Okay, you cannot make use of the formula or the power rule for the derivative of u to the n, because in u to the n, the exponent is a constant. We cannot make use of the formula for the derivative of a to the u, because in a to the u, the base is a constant. So what we can use here is implicit differentiation, but the very first step is to take the natural logarithm of both sides of the equation. And in this case, we'll have ln of y on the left side, and on the right side is ln of x raised to x. Okay, that's always the first step. So we recall one of the properties of logarithms wherein ln of a raised to r can be written as r ln of a. So therefore, we can write the function as ln of y equals x ln of x. So this is now a function in its implicit form because y is not written in terms of x only. So we use implicit differentiation to get y prime. So on the left side, we have the form ln of u. When we differentiate with respect to x, we'll have 1 over y times the derivative of y with respect to x, which is denoted by y prime. On the right side, it involves a product of x and ln of x, so we'll use product rule. So this is u in our product rule, and this is v. Okay, so it's x times the derivative of ln of x, which is 1 over x, plus ln of x times the derivative of x with respect to x, which is 1. Okay, and then we'll solve for y prime. By multiplying both sides of the equation by y, we'll be able to cancel y out on the left side, and we'll just have y prime equals x over x is 1 on the right, okay, plus ln of x, this is ln of x, this quantity multiplied by y. But remember that y is equal to x raised to x in the given. So we can just write y as x raised to x. So y prime is equal to, I'll write x raised to x first, times 1 plus ln of x. Okay, where x raised to x is y. Alright, so we have the derivative of the function. Okay, let's have another example similar to number 6. Y equals cosine of x. This cosine of x is raised to x also. Okay, so we have a variable in the exponent and a variable base, a base containing a variable. So we take the natural logarithm of both sides of the equation, and we'll get ln of y equals ln of cosine of x raised to x. And then applying the property of logarithms that we applied in the previous example, we'll have ln of y equals x ln of cosine of x. Now the right side is a product of x and ln of cosine of x. So we use implicit differentiation again to take y prime. On the left side, we'll have 1 over y prime, which is the derivative of ln of y with respect to x. And then using product rule on the right side, wherein u is equal to x and v is equal to ln of cosine of x, we'll have x times the derivative of ln of cosine of x with respect to x, which is 1 over cosine of x, times the derivative of cosine of x, which is negative sine of x, plus ln of cosine of x times the derivative of x with respect to x. Okay, so we have y prime over y on the left side equals, well, this sine over cosine, if you recall, is equal to tangent function. So sine x over cosine of x is equal to tangent of x. So we have on the right side, first term on the right side, negative, don't forget the negative sign, x tangent of x plus ln of cosine of x. Solving for y prime, multiply both sides of the equation by y. Okay, so we'll have y prime on the left side. And then negative x tangent x plus ln of cosine of x multiplied by y. But in the given function, y is equal to cosine of x raised to x. So we'll just write y prime in terms of x only. And we'll have cosine of x raised to x times negative x tangent of x plus ln of cosine of x. Okay, this is the derivative of y with respect to x. Another example similar to example 6 and 7, y equals x raised to tangent of x. Okay, so we have a variable in the base and a variable in the exponent, so we'll use implicit differentiation for this one. First step is to take the ln of both sides of the equation. Ln of y equals ln of x raised to tangent x. Now applying the same property of logarithms, in this equation we'll have ln of y equals tangent of x times ln of x. Okay, so again we'll use product rule on the right side, and then we'll just use the formula for the derivative of ln of u on the left side. Okay, so the derivative of ln of y with respect to x is 1 over y prime equals, for the product rule, tangent x is equal to u in the product rule, and then v is equal to ln of x. So it's a tangent of x times the derivative of ln of x, which is 1 over x, plus ln of x times the derivative of tangent of x with respect to x, which is secant squared of x. Okay, now multiply both sides of the equation by y. Okay, so that y will be cancelled out on the left side of the equation, and we'll get y prime equals y times 1 over x tangent of x plus secant squared x ln of x. Okay, but in the given function, y is equal to x raised to tangent of x, so we can write y prime as x raised to tangent of x times tangent of x over x plus secant squared x ln of x. You can take the LCD inside the grouping symbol, and the LCD is x. So that's x raised to tangent of x, y prime on the left side, taking the LCD, which is x. So we'll have in the numerator tangent of x plus x secant squared x ln of x. Now we can divide x raised to tangent of x by x raised to 1. Okay, so we'll have y prime equals x raised to tangent of x over x multiplied by tangent of x plus x secant squared x times ln of x. Okay, now when we divide expressions with the same base, what we do is copy the base and subtract the exponents. Remember that the exponent of x in the denominator is 1, so we can just write y prime as x raised to tangent of x minus 1. Okay, times the same expression inside the grouping symbol plus x secant squared x ln of x. So we can avoid writing our final answers with fractions by doing this. This is the derivative of y with respect to x. Just one last example for implicit differentiation involving logarithmic and trigonometric expressions for ln of secant of y plus tangent of y. Okay, minus 2x minus sine of 2x equals an arbitrary constant c. So we have to find y prime again. Okay, so this function is in implicit form, so we'll have to use implicit differentiation to find y prime. Okay, we have 3 terms on the left side. We'll just have to differentiate all the 3 terms on the left side with respect to x. And then on the right side, it's just a constant. So we'll just get the 0 on the right side upon differentiation. Okay, so On the left side, first term, we have 4 ln of secant of y plus tangent of y. So this is in the form ln of u, where u is equal to secant of y, tangent of y. So don't mind the constant 4, we'll just copy that. So the derivative is 4 times the derivative of ln of u. So it's in the form 1 over u, secant of y plus tangent of y, times du. And that is the derivative of secant of y plus tangent of y. So secant of y, derivative of that is secant of y tangent of y times y prime, which is the derivative of the angle, plus the derivative of tangent of y, which is secant squared of y times y prime. Alright, now we go to the second term, minus 2x. So minus the derivative of 2x with respect to x, which is just 2, minus the derivative of sine of 2x, which is cosine of 2x, times the derivative of the angle, 2x, which is 2, equals the derivative of a constant, which is 0. Okay, we'll just solve for y prime. Next thing to do is distribute 4 over secant y plus tangent y inside the parenthesis. Okay, so that's what we're going to do in the next step. So we'll have 4 secant y tangent of y times y prime over secant of y plus tangent of y, plus 4 secant squared of y times y prime over secant of y plus tangent of y. Okay, minus 2 cosine of 2x equals 0. The next step is to transpose all the terms without y prime on the other side of the equation. So 2 or minus 2 and minus 2 cosine of 2x must be transposed to the other side. And then on the left side, we have to factor out y prime from these two terms. And so we'll have y prime factored out. So 4 secant y tangent y over secant y plus tangent y in the first term. While in the second term, we'll have 4 secant squared of y over secant of y plus tangent of y. On the right side, we'll have 2 plus 2 cosine of 2x. Now to solve for y prime, you'll just have to divide both sides of the equation by the expression inside the brackets. Okay, remember the two terms inside the bracket, set of brackets is, or I mean they have the same denominator, so we can just write them as a single rational expression. Okay, so y prime is just multiplied by 4 secant y tangent y plus 4 secant squared of y all over the same denominator, secant of y plus tangent of y. Okay, we can factor out 2 from from the other side of the equation. 2 times 1 plus cosine of 2x. Right, so dividing both sides of the equation by the expression inside the set of brackets, we'll have y prime equals, that's 2 times the quantity 1 plus cosine of 2x over the expression inside the bracket 4 secant of y tangent of y plus 4 secant squared of y all over secant of y plus tangent of y. Okay, so now we'll have, upon simplification, we'll have y prime equals, this 4 can be factored out also. Take note. Okay, I encircled the number 4, so we can factor that out. And then when we divide fractions, what we do is get the reciprocal of the denominator and proceed to multiplication. So you'll have, in this step, you'll have 2 times 1 plus cosine of 2x. I just copy the numerator. And then this part will go to the numerator also upon getting the reciprocal of the denominator. So we'll have 2 times 1 plus cosine of 2x times secant of y plus tangent of y over, now 4 is factored out, okay, secant of y times tangent of y plus secant squared of y. I factored out 4 so that we can divide 2 by 4, and when you simplify, we'll have 1/2 only instead of 2 over 4. Alright? So just rewriting y prime, we have 1 plus cosine of 2x times secant of y plus tangent of y all over 2 times secant of y tangent of y plus secant squared of y. Okay? You may opt to factor out secant of y here from these two terms in the denominator, and we'll write the answer as y prime equals 1 plus cosine of 2x times secant of y plus tangent of y all over 2 times secant of y times the quantity tangent of y plus secant of y. Okay, in factored form, this is the derivative of y with respect to x. Oh wait, we can still simplify this. So we have cancelled out secant of y plus tangent of y. Okay, so when simplified, we'll get y prime equals 1 plus cosine of 2x over 2 secant of y. Okay, I hope I was very clear on what I did at the bottom part. Just going back to this. Okay, what I did was factor out secant y from both terms in the denominator. And then we obtained this expression, secant y plus tangent y in the numerator, and also the same expression in the denominator. So when I divided, we'll just get, we got 1. So when simplified, what we had is y prime equals 1 plus cosine 2x over 2 secant y. Okay, now remember that the reciprocal of secant function is cosine function. So 1 over secant y may be written as cosine of y. Okay, so y prime may now be written as 1 plus cosine of 2x over 2, okay, times cosine of y. Okay, because 1 over secant y is equal to cosine of y. So we can just have y prime as, when we distribute cosine of y, we'll have cosine of y, okay, plus cosine of y, cosine of 2x over 2. Okay, so we can just write our derivative in this form. This is y prime. Or you may write the derivative by factoring out cosine of y from both terms in the numerator. It's just the same thing in factored form, okay? This is y prime, the derivative of y with respect to x.